It is a profound, almost unsettling truth that our cosmic maps, for all their stunning detail, are maps of populated places. They chart the vibrant star cities of galaxies, the sprawling metropolitan clusters they gather in, and the great filaments of matter that connect them in a web of light. We navigate by these beacons, these assemblies of billions of suns, and in doing so, we have quietly accepted a galactic perspective, that to be in the universe is to belong. To orbit a star, which belongs to a galaxy, which belongs to a group, which is drawn along a filament to a cluster. It is a nested existence, a cosmic address of increasing scale. But this map, for all its grandeur, is also a map of bias. It illuminates where the matter is, where the action resides, and in its glowing contours, it implies that the vast volumes between these luminous structures are nothing but a silent, empty void, a mere backdrop to the main event. This is the intergalactic medium, a space so tenuous it makes the vacuum of our own solar system seem thick and cluttered by comparison. It is here, in this profound and echoing darkness, far from the gravitational pull and the stellar light of any galaxy, that we must recalibrate our imagination. For recent observations, subtle and patient, have begun to whisper of inhabitants in this void. Not swarms of them, not civilizations, but solitary, profound, and deeply lonely worlds, planets, adrift in the abyss between galaxies. To contemplate such an object, a lonely planet between galaxies, is to engage with the story of cosmic ejection, of gravitational violence, of a solitude so complete and so ancient that it challenges our very understanding of what a world is and where a world can be. Imagine, if you can, the vantage point. You are not on a telescope platform on Earth, but a silent, invisible point suspended in the intergalactic deep, behind you and in front of you, and to all sides, the darkness is absolute. Not the gentle black of a moonless night sky, which is still punctuated by thousands of stellar pinpricks, but a blackness so total it feels like a substance. It is the black of empty space, diluted to near perfection. Here, the density of matter can be less than a single atom per cubic meter. The cosmic microwave background radiation, the afterglow of the Big Bang, is the dominant source of energy, a uniform whisper of warmth just a few degrees above absolute zero. There is no day, for there is no sun. There is no year, for there is no orbit. There is only the endless, unvarying fall through a darkness older than most stars in the galactic disk you once called home. The timekeeping of such a world is not marked by sunrise or sunset, or the procession of constellations, for the constellations do not exist. The entire sky, from every angle, would be a sparse and unmoving tapestry of faint, fuzzy blobs, the distant, unreachable galaxies. They would not twinkle, for there is no atmosphere to distort their light. They would simply hang, immutable and faint, like ghostly island universes, receding forever in an infinite sea. The primary source of light on the surface of such a planet, if it even has a surface, would be this eerie galactic glow, a dull, cold illumination from a billion distant suns, blended into a soft, directionless haze. It would be insufficient to cast a shadow, insufficient for photosynthesis, insufficient for anything but the faintest hint of a landscape, if one could perceive it at all. The cold would be profound, a deep and sinking chill measured in single digits above absolute zero. As any internal heat from formation slowly, inevitably bleeds away into the void, how does a world come to find itself in such an exile? The genesis of these intergalactic orphans is not a gentle one. They are not born in the quiet outskirts of a galactic suburb. They are violently evicted from the metropolitan center. The leading mechanism, supported by complex N-body simulations run on some of the world's most powerful supercomputers, involves the gravitational dynamics of dense stellar environments. Within the core of a galaxy, particularly during its early, chaotic history, or during a major merger with another galaxy. Stars can engage in a complex gravitational dance. When multiple massive bodies interact, their gravitational pulls can slingshot one another with tremendous force. In most cases, this results in a rearrangement of orbits, but in a rare, precise, and devastating alignment, one of the bodies, often the least massive, can be accelerated to a velocity exceeding the galactic escape velocity. It is flung out, not just from its stellar neighborhood, but from the gravitational grasp of the galaxy itself. This is a hypervelocity star, and if that star has planets in orbit around it, they are taken along for the ride, clinging to their parent sun as it is catapulted into the intergalactic void. Another, perhaps more lonely scenario involves the planet itself being the target of a gravitational slingshot. In a young, unstable planetary system, the gravitational influence of a passing star can perturb the orbits of planets, ejecting one entirely. If this ejection is powerful enough, the planet could be thrown free of its star and its galaxy in one terrible event, becoming a true rogue, a dark world with no sun, set on an eternal trajectory through nothingness. These processes are not speculative fiction. We have observed the stellar component. Telescopes have identified hypervelocity stars, like the famous S5 HVS1, a star rocketing through the halo of our own Milky Way at over 1,700 kilometers per second, destined for the great beyond. Where a star can go, its planets can follow. And where a star is not present, a planet may still travel alone. The very nature of such a planet defies our terrestrial expectations. Without the steady influx of stellar energy, its internal composition and any residual heat become the sole determinants of its condition. A gas giant, like a Jupiter or Neptune ejected early in its life, might retain a thick, dense atmosphere of hydrogen and helium. But over billions of years, even this atmosphere would slowly cool and contract, its outer layers potentially freezing into exotic forms of precipitation. Helium rain, perhaps, falling through layers of metallic hydrogen. A terrestrial world, an ejected Earth or super-Earth, would rapidly become an ice-locked tomb. Any atmosphere would freeze out, collapsing as snow onto a surface of perpetual night. Any oceans would become global ice sheets kilometers thick, not over water, but over a solid bedrock shell. Yet beneath that ice, a possibility lingers, a whisper from studies of worlds like Europa or Enceladus. Radioactive decay in the planet's core, left over from its violent formation, could provide a slow, steady trickle of geothermal heat for billions of years. This heat, trapped beneath an insulating shell of ice and rock, might be enough to maintain a vast, dark, subsurface ocean of liquid water, an abyssal sea never touched by starlight, its chemistry fueled by hydrothermal vents on an ocean floor that has never known a sun. In that profound darkness, in that crushing pressure and eternal warmth, the basic ingredients for life, water, energy, chemistry could, in theory, persist. It is a haunting thought that the most isolated, the most lonely planet in the universe could, against all odds, cradle a biosphere in its deep, warm heart. A biosphere that would evolve in total isolation, unaware of a sky, of stars, of anything beyond the slow convection currents of its dark ocean and the mineral-rich plumes from its core. Its only sense of the wider cosmos might be the faint, steady tremors of gravitational waves from merging black holes in distant galaxies, passing through the planetary body like a silent cosmic bell being rung. To detect such a lonely wanderer is an exercise in pushing observational astronomy to its absolute limits, a search for a single, cold, dark pixel in a cosmos saturated with light. We cannot see it directly, for it emits no light of its own, save for the infinitesimal trickle of residual thermal radiation, a glow so faint and so redshifted by its possible motion, and the expansion of space itself, that it is drowned in the cosmic microwave background. We must instead look for its rare and fleeting interactions with the few sources of illumination that exist in the intergalactic void. The primary method relies on a phenomenon that feels almost like a cosmic kindness, a momentary betrayal of the planet's perfect solitude, gravitational microlensing. This elegant principle of Einstein's general relativity states that a massive object, warping the fabric of space-time around it, can act as a lens. When such an object passes almost exactly between a distant, bright background source like a star in another galaxy, or better yet, a brilliant quasar and our telescopes, it briefly magnifies the background light. For a star, this event can last weeks. For a planet-sized mass, adrift in intergalactic space, the alignment is so precise and the relative motion so specific that the event might last only a few hours, perhaps a day. It would be a tiny, almost imperceptible blip in the light curve of a source that is itself a pinprick of light from billions of light years away. Identifying such a signal requires monitoring millions of these background sources continuously for years. Projects like the Optical Gravitational Lensing Experiment, OGLE, and the Korea Microlensing Telescope Network, KMTNet, have honed this technique within our own galaxy, discovering a population of rogue planets drifting between the stars. But to extend this search into the intergalactic medium is a task of another magnitude entirely. It would require a dedicated, wide-field, space-based observatory with exquisitely precise photometry, staring for years at the dark patches between galaxy clusters, waiting for the 1 in a billion alignment that signals the passage of a dark, lonely world. There is another, more speculative possibility for detection, one that speaks to the planet's potential hidden activity. If, against all odds, such a rogue planet harbors a subsurface ocean warmed by geothermal forces, and if that ocean world possesses a metallic core that still churns, it could generate a magnetic field. This magnetosphere, extending out into the near-perfect vacuum, would be a silent, invisible bubble in the intergalactic medium. The intergalactic space is not entirely empty. It is threaded with extremely diffuse plasmas and magnetic fields of its own, remnants from galactic outflows, and the large-scale structure of the universe. The interaction between a planetary magnetosphere and this flowing intergalactic medium could, in theory, generate faint, low-frequency radio emissions. It would be a whisper within a whisper, a signal so weak that our current radio telescopes, designed to catch the roaring emissions of quasars and the periodic pulses of neutron stars, would almost certainly miss it. But the next generation of radio observatories, like the Square Kilometer Array, SKA, promises sensitivity to fainter and more complex signals than ever before. It is not impossible to imagine a future where a sophisticated algorithm, sifting through petabytes of SKA data of an apparently empty patch of sky, identifies a persistent, anomalously localized, and very quiet radio source, a source with no optical counterpart, no X-ray signature, just a calm, steady emission consistent with a planetary magnetosphere plowing through the tenuous intergalactic winds. The detection would be indirect, inferential, but monumental. It would not give us a picture of the world, but a confirmation of its presence, its physicality, its magnetic heartbeat in the dark. Contemplating the journey of such a planet forces us to stretch our understanding of time to scales that are genuinely cosmological. The ejection event that sent it on its solitary path likely occurred in the early universe, during the era of peak galactic construction and violence, perhaps 8, 9, even 10 billion years ago. Since that cataclysmic moment, it has been traveling. Its velocity, imparted by the gravitational slingshot, would be on the order of hundreds of kilometers per second, a blistering speed by human standards, but a crawl on the galactic canvas. At 700 kilometers per second, It would take approximately 4 million years to travel just 1 kiloparsec, a mere step within a galaxy. But given the vast distances between galaxies, millions of parsecs, it has had all the time in the universe. For billions of years, it has been in transit, a silent ship on a voyage between islands and an archipelago it will never reach. During this time, the universe around it has evolved dramatically. Galaxies that were once bright and blue with star formation have reddened and quieted. Collisions have reshaped galactic architectures. The very expansion of space has stretched the distances between the receding islands, making its intended target, if it ever had one, move further away. The planet is a relic, a time capsule not from a specific era, but from a state of the cosmos. Its composition is frozen from the time of its formation in the galactic disk, a snapshot of the protoplanetary disk chemistry of a star that may have long since died. It has been untouched by the later enrichment of the interstellar medium from supernovae. Its surface, if we could see it, would show a primordial geology, unaltered by weathering or tectonics, driven by a parent star's tides. It is a museum of the early galactic environment, preserved in the deep freeze of intergalactic space. This profound solitude invites a philosophical, almost existential line of inquiry. We define habitability by a golden rule of orbital distance from a star, not too close, not too far, within the circumstellar habitable zone where liquid water can persist on a surface. The discovery of Europa and Enceladus expanded that definition to include worlds heated from within, worlds that could possess habitable zones defined not by sunlight, but by geology. The lonely intergalactic planet takes this to the ultimate extreme. It severs the last tether to stellar-centric life. It proposes that the ingredients for a biosphere, a rocky core with radioactive elements, water, and a stable environment, can exist in complete independence from any star. This radically democratizes the potential for life in the universe. If life can begin and persist in the warm, dark depths of an exiled world, then the number of potential abodes explodes by orders of magnitude. Stars become almost incidental. Galaxies become merely the factories that produce these life-bearing seeds and then, through gravitational violence, scatter them into the void. The universe in this view is not just populated in its bright, stellar cities, but also, and perhaps predominantly, in its darkest, most isolated expanses. Each rogue planet becomes a potential ark carrying the possibility of biology on a journey that may last longer than the lifetime of its parent galaxy. And in the far, far future, as stars burn out and galaxies grow dark, these rogue worlds, with their internal heat sources decaying over trillions of years, could be the last hospitable environments in the entire cosmos, the final refuges for any form of persistent complexity in an era of profound darkness and dispersal. They are not just outliers. They may be the ultimate survivors. Yet, the very forces that create them also dictate a universe that is, for the most part, empty. Current estimates from galactic simulation models suggest that the number of planets ejected into intergalactic space could be staggering, potentially, in the trillions per galaxy over its lifetime. This would mean that the great voids between galaxies are not entirely empty. They are sprinkled, faintly and distantly, with these dark wanderers. They form an unseen, frozen population, a ghostly demographic of the cosmos that outweighs, by some calculations, all the planets bound to stars. This is a humbling and counterintuitive conclusion, that the most common type of planetary environment in the universe is not a sun-warmed world in a galactic disk, but a cold, dark, isolated sphere drifting in nothingness. Our solar system, with its brilliant sun and orbiting planets, is the cosmic equivalent of a vibrant, bustling city square. It is what we know, what we consider normal. But statistically, we are the outliers. The true normal, the median experience of a planet in our universe, is one of unimaginable cold, darkness, and solitude. This shifts our perspective from a galaxy-centric view to a truly universal one. When we look up at the dark patches between the stars, and especially at the deeper darkness between the galaxies, we are not looking at mere emptiness. We are looking at a realm that is, in its own quiet and profound way, populated. It is a frontier that is almost entirely unexplored, not because it is devoid of interest, but because its inhabitants are so perfectly hidden, their signatures so subliminally faint, that they exist at the very edge of our observational capabilities and our imagination. To study them is not just to find new planets. It is to understand the final destiny of most planetary mass in the cosmos, and to confront the possibility that life, in its most tenacious form, may prefer, or at least endure, the deepest quiet the universe has to offer. The narrative of the lonely planet is not confined to the present era or the distant future. Its origins are buried in the chaotic dawn of galactic assembly, a period when the universe was a crucible of formation and destruction. To understand the genesis of these exiles, we must journey back to the epoch of the first galaxies, when the cosmos was smaller, denser, and far more violent.
In these nascent structures, the first generations of stars, population 3 stars, were monstrous behemoths, hundreds of times the mass of our Sun, living fast and dying in spectacular pair instability supernovae that left no remnant, scattering their heavy elements into the primordial gas. Within the dense, turbulent clouds enriched by these first explosions, the second generation of stars and their accompanying protoplanetary disks began to form. It was in these early disks, around stars that were themselves often members of tight, unstable clusters, that the first planets coalesced. The galactic environment then was not the relatively orderly, slowly rotating disk we see today in mature spirals like the Milky Way. It was a clumpy, dynamic, and fiercely energetic place, with frequent close encounters between stars, and the ever-present gravitational threat of merging subgalactic building blocks. In such an environment, the delicate orbital dance of young planets was easily disrupted. A passing star in the cluster could perturb a nascent giant planet, sending it on a wildly eccentric path that would destabilize the entire inner system, potentially ejecting terrestrial siblings outward. Or, during a major merger of 2 small proto-galaxies, the combined gravitational potential would undergo a violent relaxation, a cosmic reshuffling where stars and any attendant planets were thrown onto new, often unbound, trajectories. Simulations of these early eras show a prolific production of free-floating planetary mass objects, with many of them receiving velocities sufficient to escape not just their stellar system, but the shallow gravitational well of the young galaxy entirely. They were launched into the proto-intergalactic medium, which at that time was richer in gas and dust, but still an unimaginably vast emptiness. These first-generation exiles are the true ancient mariners, travelers that have witnessed, from their silent vantage, the entire growth and maturation of the cosmic web, from its first faint strands to the great, glittering filaments we see today. Their surfaces, if they are solid, are time capsules of the very first solid materials to condense in the universe, perhaps even containing isotopic ratios of elements that tell the story of the very first supernovae. As we consider the potential internal dynamics of such a world, the role of tidal forces, or rather, the crushing lack thereof, becomes a defining characteristic. In our solar system, the geological and thermal activity of moons like Io and Europa are driven by tidal heating, the constant, rhythmic flexing induced by the gravitational pull of their massive parent planet. A planet bound to a star also experiences subtle tidal effects, contributing to internal heat and orbital evolution. But for the lonely planet between galaxies, tidal forces are virtually non-existent. The gravitational pull from the nearest galaxy is so diffuse and uniform across the planet's body as to be imperceptible. There are no monthly cycles of stress and release, no rhythmic squeezing of its interior. Its heat budget is therefore governed solely by 2 factors: the primordial heat from its accretion and differentiation, and the long-lived radiogenic heat from the decay of isotopes like uranium-238, thorium-232, and potassium-40 within its mantle and core. This presents a slow, inexorable cooling curve, a thermodynamic fate plotted over hundreds of billions of years. For a large terrestrial world, a super-Earth with a massive iron core and a thick silicate mantle, this radiogenic heating can be significant. Models suggest that such a world, even after 10 billion years of exile, could maintain a partially molten outer core, sustaining a global magnetic dynamo, and a mantle warm enough for convective currents. This slow convection could drive a form of plate tectonics, or more likely, a single shell, stagnant lid tectonics with sporadic volcanic outgassing. Any atmosphere such a planet retained after ejection, a possibility if it was a gas giant, or a terrestrial world with a sufficiently strong gravitational hold and a calm, nonviolent ejection, would be subject to a different kind of erosion. Without a stellar wind to strip it away, the primary atmospheric loss mechanisms would be thermal escape of the lightest gases and, over cosmologically vast timescales, the cumulative effect of individual cosmic ray impacts. The atmosphere would likely stabilize into a thin, uniform cloak, possibly dominated by heavy inert gases like argon or xenon, or, if volcanic outgassing persists, nitrogen and carbon dioxide. On such a world, the sky would not be black, but a deep, perpetual twilight purple or gray, illuminated only by the integrated light of distant galaxies, filtered through this permanent, thin haze.
Pressure would be low, temperatures would be a uniform and deadly cold, and the only weather might be the slow sedimentation of atmospheric gases as frost, creating endless, rolling dunes of frozen nitrogen or carbon dioxide snow over landscapes of ancient, unweathered rock. The concept of a biosphere in such an environment stretches the definition of life to its theoretical limits, yet it remains a compelling frontier for astrobiology. The canonical requirements are water, a source of energy, and a suite of essential elements. The lonely planet could, in its deep subsurface ocean, meet all three. The energy source is not photons, but chemistry and radioactivity. At the rocky floor of a subsurface ocean, hydrothermal vent systems driven by the planet's internal heat would provide a constant flux of reducing chemicals like hydrogen sulfide, methane, and hydrogen dissolved in superheated water. These chemicals, in the presence of minerals that can act as catalysts, could drive chemosynthetic reactions, providing the foundational energy for a microbial ecosystem, much as they do around Earth's deep-sea vents. This ecosystem would exist in a state of profound energy limitation, a slow-motion metabolism, where every reaction is measured against the slow decay of planetary isotopes. Evolution in such a setting would be driven not by competition for sunlight or seasonal change, but by competition for access to the mineral-rich vent fluids. Life forms might evolve to be extraordinarily efficient, with metabolisms operating at rates we would perceive as geological. Their sense of time would be calibrated to the convection cycles of the mantle and the slow cooling of the core. They would have no circadian rhythms, for there is no day. They would have no concept of direction, for there is no up or down in a buoyant ocean under ice, and no celestial navigation. Their entire universe would be the dark water, the thermal plumes, and the mineral-laden chimneys. Communication, if it existed, would likely be chemical or perhaps electrical, tuned to the low-frequency sounds of shifting ice and rumbling rock. It is a biology of pure interiority, a civilization, if such a word could ever apply, that is literally and figuratively inward-looking. Its collective intelligence, should it arise, focused on the mysteries of its own planetary heart rather than the irrelevant void above the ice ceiling. The very thought experiment forces us to decouple intelligence from curiosity about the cosmos. For the cosmos, to such beings, is an abstract, unreachable, and featureless non-entity. Their cosmology would be one of heat flow and chemical gradients. Their gods, perhaps the mysterious, periodic tremors that ripple through their world, unaware that those tremors are the faint echoes of colliding black holes 100 million light-years away. For a moment, let us shift perspective from the planet itself to the view from its imagined surface, a perceptual exercise that dissolves our anthropocentric biases. Standing on this world, the sky is not a dome, but a sphere of utter blackness, a perfect void. And yet, it is not empty. It is studded with the faint, fuzzy smudges of galaxies, each containing hundreds of billions of stars. But these smudges do not move. There is no rotation of the sky, no rising or setting of any object. The planet's own rotation might still exist, a leftover spin from its formation, but with no sun to mark its passage. The concept of a day is meaningless. The galaxies are fixed in their positions, their apparent arrangement changing only over millions of years due to the planet's own slow, proper motion through the void. The Milky Way, if it could even be identified as such, would be just one among thousands of similar, faint, elongated glows. There would be no constellations, for the familiar patterns are formed by stars within our own galaxy. Here, the landmarks are entire island universes. The Andromeda Galaxy might appear as a slightly brighter, tilted oval. The Virgo cluster would be a dense, confused knot of faint light. The sky offers no navigation, no seasons, no timekeeping. It is a static, eternal museum diorama of the large-scale structure of the universe. The only changes in the sky would be events of unimaginable rarity and power. A nearby supernova within one of those distant galaxies might, for a few weeks, outshine the entire combined light of its host, appearing as a new, temporary star in the otherwise immutable tableau. Or, the slow, patient drift of a foreground galaxy might, over eons, pass directly in front of a background quasar, causing a gravitational lensing event that would gradually brighten and then fade a specific point of light over centuries, a light show whose full arc no individual observer could ever witness. The dominant sensory experience would be one of immense, crushing silence and stillness, broken only by the planet's own internal sounds. The groan of ice, the rumble of a distant magma shift, the hiss of gases escaping from a fissure. It is a landscape of perfect geological patience, where a mountain range might stand for 100 billion years without being eroded by wind or rain, its sharp peaks silhouetted against the eternal galactic glow. The trajectory of a lonely planet is not a straight line through a static grid, for it moves within a universe that is itself stretching, expanding, and evolving on the grandest scales. Its path is a subtle curve through space-time, influenced by the cumulative gravitational pull of the entire cosmic web, a whisper of a tug from a filament of dark matter hundreds of millions of light-years away, a faint deflection from the aggregated mass of a distant supercluster. This journey, over billions of years, is a form of cosmic drift, a slow-motion ballet where the dancer is unaware of the stage. Unlike a comet flung from the Oort cloud that might one day return on a vast elliptical orbit, the intergalactic rogue has no home to return to. Its ejection velocity, combined with the expansion of space, ensures it is on a one-way journey into deepening isolation. There is a profound and irreversible asymmetry to its existence. It began in a place of light, heat, and complex gravitational interaction, and it is headed toward a future of increasing darkness, cold, and gravitational uniformity. As it travels, the galaxies it passes, or more accurately, that it slowly moves relative to recede from it and from each other due to the Hubble flow. The very metric of space between it and any point of reference is growing. The faint, fuzzy glows in its sky will, over hundreds of billions of years, redshift further and further, their light dimming and stretching into insignificance. In the far future, as described by models of cosmological evolution, all galaxies beyond the local group will have disappeared beyond the cosmic light horizon. For our lonely planet, this process happens even faster. Long before the stars of the Milky Way burn out, its view of external galaxies will have faded to near nothingness. Its sky will then become truly, perfectly black, save for the uniform, cold glow of the cosmic microwave background, which itself will have redshifted into undetectability. The planet will then be adrift in a void so complete that not even the evidence of other structures remains. It will become an island not just in space, but in information, utterly disconnected from the rest of cosmic history. This is the ultimate fate of the intergalactic exile, to become a silent, dark monolith in a universe that has forgotten how to make light, its only companion, the inevitable decay of its own internal heat. Yet, within this narrative of cooling and darkening, there exists a paradoxical potential for transient, eerie phenomena. Consider the possibility of a cryovolcanic eruption on a world with a subsurface ocean. On a bound moon like Enceladus, such eruptions are driven by tidal forces and create magnificent plumes. On our lonely planet, the driving force would be the slow buildup of pressure from freezing expansion or the accumulation of radiogenic gases. Without an atmosphere to speak of, an eruption would not create a plume in the conventional sense. Instead, liquid water, superheated by the planet's internal warmth, but still well below 0 Celsius due to the ambient vacuum pressure, would instantly flash into a mixture of vapor and ice crystals. In the profound cold and absence of wind, this vapor would not rise far. It would form a localized, temporary, and faint fog around the vent, a cloud that would slowly precipitate as fine, black ice, colored by dissolved minerals and organics from the ocean, back onto the surface. Under the only available illumination, the integrated light of distant galaxies, this event might be utterly undetectable from even a short distance away. But if such an eruption were to occur on a world that retained a thin atmosphere, the results could be more dramatic. The sudden injection of volatiles could create a temporary, localized atmospheric patch, a tenuous hood that might, for a few centuries or millennia, refract and scatter the galactic light in strange, faint halos or auroral glows, powered not by a solar wind, but by the interaction of the planet's residual magnetic field with the newly released ions. These would be ghostly, slow-motion weather events, their cycles measured in geologic time, visible only to an observer standing on that very surface, an observer who will never exist. The planet's geology, in the absence of external erosion, would be a record of such internal events alone. Mountain ranges would be built by slow, episodic volcanic outpourings over aeons. Canyons would be carved not by rivers, but by the gradual tectonic cracking of the global ice shell. The landscape would be one of extreme, pristine clarity, with features standing in sharp relief for time spans that dwarf the entire history of life on Earth. Their shadows cast not by a sun, but by the directionless, milky glow of a universe of distant galaxies. The search for these objects is more than a technical challenge. It is a philosophical imperative that tests the limits of our scientific reach. Current microlensing surveys are not optimized for the intergalactic regime. They focus on dense stellar fields, the galactic bulge, and the Magellanic Clouds, where the chance of a lensing event is high because of the sheer number of background stars. To search the true voids, we must look through them at even more distant background sources, the unresolved continuum of a faraway galaxy, or the compact, brilliant beacon of a quasar. This requires a different statistical approach. Instead of looking for individual, well-defined events, astronomers might look for a collective signal, a subtle, excess flickering in the light of thousands of quasars, a statistical signature that a population of dark, planetary mass objects is drifting through the lines of sight. This is a measurement of the optical depth to microlensing imposed by the intergalactic population. It is a daunting task, requiring control over innumerable variables, from intrinsic quasar variability to the subtle effects of interstellar dust in the foreground galaxies. Yet, it is not impossible. The upcoming Vera C, Rubin Observatory's Legacy Survey of Space and Time, LSST, will monitor the entire southern sky with unprecedented depth and frequency. While its primary goals are dark energy and solar system science, its immense dataset, a motion picture of the sky over a decade, will contain, buried within the petabyte streams, the fingerprints of transient events in every environment, including the dark voids. Machine learning algorithms, trained to recognize the specific, smooth, symmetric light curve of a microlensing event, will sift through this data. A handful of candidate events where the lens is determined to be far in the foreground of any known galaxy could represent the first tentative detections of this population. They would not be glamorous, headline-grabbing pictures of a world, but rather a line in a catalog of anomalies, a line with a redshift parameter noted as intergalactic, followed by a question mark. The confirmation would likely come later, from coordinated observations with the James Webb Space Telescope or the next-generation 30-meter class ground-based telescopes, attempting to catch the faint, thermal emission of the lens itself in the mid-infrared, a nearly hopeless endeavor, but one that might yield a marginal detection if the object is fortuitously close and still slightly warm. Beyond pure detection, the study of these worlds, should we ever develop the technology to probe them directly, would revolutionize planetary science. A planet that has never been bathed in intense ultraviolet radiation from a star, never subjected to the chemical alteration of stellar winds, and never experienced the gravitational kneading of a tidal partner, is a pristine laboratory. Its atmospheric composition, if it has one, would reflect the primordial outgassing of its interior and the freeze-out sequence of gases in the ultimate cold trap. Its surface chemistry would be unweathered, showing the bare mineralogy of its crust as it formed. For a gas giant rogue, its atmospheric layers would be stratified by temperature and pressure alone, without the complicating factor of external irradiation driving photochemistry and global circulation patterns. Measuring the deuterium to hydrogen ratio, or the abundances of noble gases, in such an object would give us a clean reading of the conditions in the protoplanetary disk of its origin, unfiltered by billions of years of stellar processing. These measurements could tell us which galaxy it came from, or at least the type of galactic environment it was born in. An orphan could, paradoxically, reveal more about its lost family than many planets that stayed at home. Furthermore, the very existence and estimated number density of these objects serve as a powerful constraint on models of planetary system formation and early galactic dynamics. If we find that the intergalactic void is teeming with rogue planets, it implies that the process of planetary ejection is extraordinarily efficient, and that our own calm solar system may be a rare, stable outcome. If we find them to be exceedingly rare, it suggests that planetary systems are generally gravitationally robust, or that ejection velocities rarely reach the galactic escape threshold. In either case, the senses of the darkest, most isolated places in the universe holds a mirror up to the bright, chaotic stellar nurseries where planets are born, revealing fundamental truths about the violence and generosity of cosmic beginnings. The concept of these wandering worlds inevitably leads us to a broader, more speculative vista, the cosmic ecology of dark matter and its enigmatic relationship with baryonic matter, the stuff of planets and stars. The lonely planet, composed of familiar elements, drifts through a sea that is predominantly made of something else. The intergalactic void is not empty of mass. It is, in fact, filled with the tenuous filaments of the cosmic web, which are predominantly composed of dark matter. This mysterious substance, which interacts only through gravity and possibly the weak nuclear force, forms the underlying skeleton of the universe. The planet's journey, therefore, is a passage through a ghostly landscape of dark matter halos, streams, and subhalos, entirely imperceptible to its physical form. It feels no drag, no friction, no direct encounter. Yet its path is subtly shaped by the gravitational gradients of these unseen structures. In a profound sense, the planet is a speck of luminous matter, or at least matter that was once luminous, navigating the invisible architecture of the cosmos. This dichotomy highlights a fundamental segregation in the universe. During the violent ejections from galaxies, dark matter, which does not experience hydrodynamic forces or collisions, remains bound to the galactic halo. The planet, a clump of baryons, is stripped away. Thus, the exile is not just from light and community, but also from the dominant form of matter in its home galaxy. It becomes a purely baryonic entity in a dark matter universe, a tiny island of complex atomic chemistry, adrift in a sea of unknown particles. This separation may have profound implications for its ultimate evolution. Some theories of dark matter, such as those involving macroscopic compact halo objects, MACOs, or a spectrum of primordial black holes, suggest that dark matter could clump into planet mass objects itself. If true, our lonely planet might, over an astronomically long period, have a gravitational encounter with one of these dark counterparts. The event would be utterly silent and invisible, a mere deflection in the void, a slight change in the cold trajectory of the world, a whisper of an interaction between the known and the unknown. It is a reminder that the planet's solitude is not merely an absence of light, but an existence at the frontier between the understood and the deeply mysterious components of physical reality. Let us now descend, in imagination, to the surface of a specific archetype of this lonely world, a super-Earth, 2 times the mass of our own planet, ejected in the early universe. Now 5 billion years into its exile, it possesses a thick, global ice shell, 50 kilometers thick, insulating a subsurface saltwater ocean of another 100 kilometers depth, which rests upon a silicate mantle and a still molten iron core. The pressure at the ocean floor is immense, yet the water remains liquid due to the antifreeze properties of dissolved salts and ammonia, and the gentle, pervasive geothermal warmth from below. In this eternal darkness, there is no photosynthesis, but around hydrothermal vents on the ocean floor, structures of porous, warm rock, where reduced minerals like sulfides leach into the water, a chemosynthetic ecosystem could have arisen. The base of the food web would be microorganisms analogous to Earth's archaea, oxidizing hydrogen or methane to fix carbon. These microbes might form dense, living mats on the vent chimneys, their metabolism so slow that cell division might occur once per century. Filter-feeding organisms with delicate gossamer structures to harvest the sparse microbial snowfall could drift in the still currents. Predators, if they exist, would be ambush hunters, conserving energy for bursts of movement triggered by the faint chemical plumes or vibrations in the water from geological activity. The entire biosphere operates on a trickle of chemical energy, a slow-burning fuse set by the planet's radiogenic heart. Evolution here is not driven by changing seasons or competition for light, but by competition for access to the mineral-rich vent fluids and the need for extreme efficiency. Sensory systems would be tuned to chemistry, pressure, and perhaps the faint electrical fields generated by moving water through the planet's magnetic field. Bioluminescence, so common in Earth's deep oceans to attract mates or prey, would be pointless in an ecosystem where every participant is blind to light. Instead, communication might involve the release of complex cocktails of molecules, or the detection of subtle changes in water conductivity. The concept of an ecosystem season would be tied to the geologic timescale of vent activity. A vent field might be active for 1 million years, then go dormant, forcing a slow migration across the ocean floor to a new site over millennia. This is a biology of profound patience, a testament to life's ability to cling to the slightest gradient, the faintest whisper of free energy, in the most isolated environment imaginable. The ultimate future of this world, and any potential biosphere, is a slow fade into absolute zero. The radiogenic isotopes that power its core and mantle have half-lives measured in billions of years. Uranium, 238 decays with a half-life of 4.5 billion years. Thorium, 232 with 14 billion years. Potassium, 40 with 1.25 billion years. Their heat output is a declining exponential. As the core cools, the magnetic dynamo will eventually cease. The convective currents in the mantle will slow and stop, and volcanism at the rock-water interface will come to an end. The hydrothermal vents will grow cold. The chemical energy that sustains the deep ocean ecosystem will vanish. The ocean itself will begin to freeze from the bottom up, as the heat flux from below can no longer counter the loss to the icy shell above. The final refuges for life would be the last pockets of liquid water trapped in the freezing matrix, perhaps sustained for a brief additional period by the exothermic energy released during the phase change of water to ice. But eventually, all liquid will solidify. The planet will become a homogeneous, frozen sphere. Its geology will be locked in stasis. Any record of its internal ocean, of its hypothetical biosphere, will be perfectly preserved in the deep freeze, a fossil on a planetary scale. In the far, far future, long after the last stars have died and galaxies have evaporated, such a world will continue on its trajectory through an ever-expanding, ever colder void. It will be one of the last baryonic structures to persist, outliving stars, nebulae, and even the black holes that will have evaporated via Hawking radiation over timescales so vast they are meaningless to contemplate. In this ultimate, dark, and cold epic, the lonely planet becomes a relic of a forgotten, vibrant era of the universe, a tombstone for the age of light and complexity, carrying within its frozen depths the potential fossilized echoes of a biology that knew only interior warmth and eternal night. Returning our gaze to the present, the search for these objects is more than a census of dark matter or a test of planetary formation models. It is an exploration of the limits of cosmic loneliness. Every physical object we have ever studied, from the dust mote to the supercluster, exists in a context of relationship, gravitational, radiative, or chemical. The lonely planet between galaxies is the closest thing to an absolute isolate that the laws of physics permit. It is a system unto itself, its history decoupled from the broader narrative of galactic evolution, its future dictated by its own slow internal clock. Studying it, or even simply contemplating its existence, forces a Copernican revolution of a different kind. Not only are we not at the center of the universe, but our condition of being bathed in light, warmed by a star, and surrounded by a celestial community may be the exception, not the rule. The typical experience of matter organized into a planet is one of darkness and solitude. This shifts our anthropic perspective. If life is possible in such a place, then our own existence on a bright, warm world orbiting a stable star is not a prerequisite for complexity. It is merely one path among many, perhaps even a privileged and easy one. The dark intergalactic ocean represents a harder, slower, more austere path, but one that the tenacity of chemistry might still traverse. The detection of even a single such world would irrevocably alter our understanding of the universe's demographic makeup. It would populate the voids with possibility. It would tell us that the cosmos is not just an archipelago of luminous islands, but also a deep, dark ocean. And in that ocean, there are solitary swimmers, carrying their own inner worlds on journeys that will outlast the stars themselves. The silence of the intergalactic medium is not the silence of absence, but the silence of isolation, a quiet so deep that within it, the slow heartbeat of a radioactive core and the whisper of a subsurface current might be the only signs of a persistent, fragile persistence against the inexorable tide of entropy and time. The existence of lonely planets between galaxies is not merely a curiosity of dynamics. It is a direct prediction of the hierarchical model of structure formation, a model that has been overwhelmingly supported by cosmic microwave background data and large-scale galaxy surveys. In this paradigm, small structures merge to form larger ones, and in the process, a fraction of their constituent mass is stripped away and flung into the intercluster or intergalactic medium. This process, known as tidal stripping, is observed in the stellar realm as the diffuse, faint glow of intracluster light stars that have been gravitationally ripped from their parent galaxies and now drift in the gravitational potential of a galaxy cluster. Planets, bound to these stars or existing as free-floating entities within galactic halos, are subject to the same forces. High-resolution cosmological simulations that now include subgrid models for planetary formation and ejection are beginning to quantify this population. These simulations suggest that the number of free-floating planetary mass objects, FFPs ejected into intergalactic space, could be immense, numbering in the quadrillions per large galaxy cluster. They form a diffuse, unseen component of the universe's mass budget, a kind of dark baryonic component that is distinct from both the luminous galaxies and the non-baryonic dark matter. Their distribution is not uniform. They trace, in a ghostly fashion, the filaments of the cosmic web, having been ejected from galaxies along the same preferential directions dictated by large-scale flows. They are the cosmic detritus of galactic building, the splinters flung from the carpenter's bench as the great structures of the universe were hammered together. This population, if confirmed, would represent a third category of cosmic object, after stars and dark matter, the unbound, isolated condensates of heavy elements wandering the architectural voids of the cosmos. Their combined mass, while insignificant compared to dark matter, could be non-negligible in the accounting of normal matter, potentially resolving a small fraction of the so-called missing baryon problem, where inventories of luminous matter fall short of cosmological predictions. Consider the implications for planetary science if we could, by some miraculous technology, retrieve a sample from such a world. The analysis would be a form of cosmic archaeology, but one divorced from any known stellar context. The isotopic ratios of its rock and ice would be a Rosetta Stone for the conditions of its birth galaxy. Elements like oxygen, magnesium, and silicon carry isotopic signatures that vary depending on the type of supernova that enriched the gas from which they formed. A planet formed in a large elliptical galaxy, which had an early, intense burst of star formation, would have a different isotopic palette than one born in a small, irregular galaxy with a slower chemical evolution. Without the confounding overlay of billions of years of stellar processing in a bound system, these signatures would be pristine. Furthermore, the planet's very composition, the ratio of rock to ice, the abundance of volatile elements like carbon, nitrogen, and sulfur would tell a story of where it formed within its original protoplanetary disk. A volatile, rich body might suggest formation beyond the snow line of its star, later scattered inward and ejected. A dry, rocky body would suggest an origin in the hot inner disk. By studying a collection of such intergalactic wanderers, we could, in theory, reconstruct a statistical atlas of planetary system architectures and chemical environments from galaxies across cosmic time, a sample unbiased by our position in the Milky Way or our reliance on studying planets still bound to their stars. It would be a direct probe of exoplanetary demographics on a truly universal scale, a census taken not from the bustling city centers, but from the drifters who have left those cities behind, carrying with them the unaltered blueprints of their origins. From the perspective of the universe itself, these planets are more than just castaways. They are potential seeds for a far future ecology. In the decaying epochs of the universe, as protons may decay and black holes evaporate over timescales of 10, 40 years and beyond, complex structures will become vanishingly rare. Yet these frozen worlds, with their stable, crystalline structures, will be among the last complex assemblies of baryonic matter to persist. In a speculative but physically grounded vision of the extreme far future, the universe becomes a expanding, ever colder vacuum populated by these ever more distant frozen planets, along with occasional brown dwarfs and the ashes of dead stars. any intelligence or complex system arising in that era, perhaps created by the descendants of civilizations from the stellar epoch, would find these worlds to be invaluable resources. They are repositories of heavy elements, stores of water ice, and potentially archives of fossilized biological information. In a universe where energy is scarce and the ability to perform work is the ultimate currency, the gravitational potential energy of such a mass, or the latent chemical energy locked in its ancient ices, could be a treasure. They might be the only landmarks in an otherwise featureless and dark expanse, waypoints for any entities capable of traversing the incredible distances. In this sense, the lonely planet of today becomes the strategic resource of a far future cosmology, its solitude temporary on a timescale so vast that it encompasses the rise and fall of all galactic civilizations. Its journey, which began with violence and ejection, may end in utility and rediscovery, not by beings from its own galactic home, but by descendants of a universe that has long since forgotten the age of stars. Returning to the present challenge of detection, the most promising avenue may lie not in isolated serendipitous microlensing, but in the cumulative gravitational effect of the entire population. This is the concept of weak gravitational lensing at the smallest scales. The combined mass of a swarm of intergalactic planets along a line of sight would induce a tiny, coherent distortion in the shapes of background galaxies. This distortion is far subtler than that caused by a galaxy cluster's dark matter halo, but it would have a distinct signature. It would be smooth, extended, and correlated with the large-scale filaments of the cosmic web, yet would lack a luminous counterpart. Next-generation weak lensing surveys, like those planned for the ESA's Euclid mission and NASA's Nancy Grace Roman Space Telescope, aim to map the distribution of dark matter with unprecedented precision. In their incredibly detailed mass maps, there may be faint, filamentary overdensities that cannot be attributed to dark matter alone, or whose detailed substructure hints at a clumpiness consistent with a population of planetary mass objects. Disentangling this signal from the smooth dark matter background and the noise intrinsic to the measurement will be a Herculean task of statistical cosmology. It would require cross-correlating the weak lensing maps with other tracers of the intergalactic medium, such as maps of diffuse X-ray emission or the Lyman alpha forest in quasar spectra. A persistent, low-significance correlation could point to the shadowy presence of this population. The evidence would be statistical, not visual, a whisper in the data that says the voids are not entirely smooth. It would be a discovery born not from a single brilliant observation, but from the patient accumulation of marginal evidence across multiple wavelengths and techniques, a consensus emerging from the noise. The contemplation of these worlds ultimately serves as a powerful metaphor for scientific exploration itself. We are, in a sense, on a lonely planet, a pale blue dot orbiting an unremarkable star in the suburbs of a spiral galaxy. Our quest to understand the cosmos is driven by an innate need to find context, to map our isolation, to see if we are alone. The search for the loneliest planets is the ultimate extension of that quest. By looking for the most isolated objects possible, we are testing the boundaries of where matter can exist, where conditions can persist, and where, against all odds, the processes of chemistry and geology might give rise to something we could recognize as a world. It is a search that forces our instruments to their limits, our models to their breaking points, and our imaginations to conceive of forms of existence utterly alien to our experience. Each time we point a telescope at a dark patch of sky between the galaxies, we are not just looking at emptiness, we are looking at a potential habitat, a fossil, a waypoint, and a mystery. We are acknowledging that the universe's story is not told only in the brilliant gatherings of stars, but also in the quiet, solitary journeys of the fragments left behind. In the silent, patient drift of a lonely planet between galaxies, we may find the most profound reflection of our own existential curiosity, a mirror held up in the dark, showing us that isolation is not emptiness, but a state brimming with hidden potential and unspoken history, waiting for the faint, patient signal of inquiry to illuminate its long, cold journey through the night. To truly fathom the scale of isolation, one must consider not just the spatial, but the temporal loneliness of such a world. On Earth, our rhythms are dictated by the cosmic clockwork of our solar system. The 24-hour spin, the 365-day orbit, the 18.6-year lunar nodal cycle, the 26,000-year precession of the equinoxes. These cycles imprint themselves on our biology, our geology, our climate, and our consciousness. For the lonely planet, all these cycles are absent. Its rotation may persist, a fossil spin from its birth, but with no sunrise to mark it, the concept of a day holds no meaning. Its journey does not orbit a center. It is a pure, linear, or more accurately, geodesic trajectory through expanding space. There are no milestones, no returns, no recurring patterns in its sky. The only temporal markers are internal: the slow decay of its radioactive heat, the imperceptibly gradual thickening of its ice shell, the episodic venting of gases from its interior over million-year intervals. This is time experienced as a slow, constant cooling, a one-way thermodynamic slide. For any hypothetical subsurface biosphere, this presents a unique evolutionary pressure. In the absence of external cycles, evolution cannot select for anticipation or rhythmic behavior. There is no advantage to a circadian clock, no need for seasonal adaptations. Instead, selection would favor extreme efficiency, the ability to enter states of suspended animation for epochs between nutrient availability and sensory systems tuned to gradients that change on geological timescales. An intelligent consciousness emerging in such an environment, a remote possibility, but a fascinating thought experiment would have a fundamentally different perception of reality. Its ontology would be based on constants, not cycles. Its mathematics might be built around integrals of slow change, rather than periodic functions. Its history would be a linear narrative of cooling and concentration, not of repeating seasons and generations. The very notion of waiting for a better time would be alien. Time is a uniform, cooling medium, not a cyclical resource. This is existence in a universe where entropy is not just a statistical law, but the dominant, perceptible driver of change, felt in the gradual hardening of the world and the slowing of all internal processes. The magnetic personality of such a world, if it retains one, becomes a solitary beacon in an unmapped sea. Generated by the churning of its molten core, this magnetosphere would be a bubble of ordered magnetic fields in the otherwise chaotic and weak intergalactic magnetic environment. These intergalactic fields, thought to be seeded by primordial processes and amplified by galactic outflows, are incredibly faint, billions of times weaker than Earth's field, and tangled on large scales. The planet's magnetosphere would carve out a tiny cavity in this diffuse magnetization. The interaction would not produce bright aurorae, as there is no dense stream of charged particles like a solar wind. Instead, it might generate an ultra-low frequency hum, a release of energy as the intergalactic plasma is deflected around the magnetic obstacle. This emission would be in the radio band, but at frequencies so low they are absorbed by Earth's ionosphere, placing them in the domain of future space-based radio telescopes. Detecting this specific signature is a task of nearly quixotic difficulty, as it requires knowing where to look and having the sensitivity to pick a coherent signal out of a vast volume. However, if the planet's path were to take it through a region of slightly denser intergalactic plasma, perhaps a fossil outflow from an ancient galactic wind, the interaction could be more pronounced, creating a temporary, faint bow shock that might accelerate particles to produce a brief, detectable burst of synchrotron radiation. This would be a chance event, a fleeting cosmic spark as the dark world plows through the ghost of a galactic sigh. It underscores the fact that the planet's environment is not a perfect vacuum. but a landscape of relics and echoes, through which it moves as a silent, dark ship, occasionally causing a ripple in mediums, too tenuous for us to easily perceive. From a cosmological perspective, these objects are witnesses to the dilution of the universe. They were born in an era when matter was denser, galaxies were closer together, and the cosmic microwave background was warmer. As they travel, the universe around them expands, stretching the very fabric of space through which they move. Their peculiar velocity, the speed imparted by their ejection, slowly decays relative to the Hubble flow, the expansion of space itself. Over tens of billions of years, they will come almost to rest relative to the expanding coordinates, their motion becoming a passive drifting apart from all other structures. They are test particles in the grand experiment of cosmic expansion, their trajectories encoding information about the history of the universe's acceleration and the distribution of mass along their path. In principle, if we could track the motion of a population of these objects with extreme precision, a task far beyond any conceivable future technology, we could map the gravitational potential of the cosmic web in 3 dimensions, using them as neutral tracers that feel gravity but emit no complicating light of their own. They would be the perfect dark matter probes, except they are made of baryons. This paradoxical role highlights their unique position. They are dark to our telescopes, yet made of familiar stuff. They feel the pull of dark structures, yet are separate from them. They exist in the liminal space between the known and the unknown, the seen and the unseen, the bound and the free. The psychological impact of contemplating these worlds is one of serene dissonance. They evoke a sense of profound tranquility in their eternal, undisturbed journey, yet also a chilling sense of abandonment. They represent the ultimate detachment. In human terms, we might project onto them feelings of loneliness or existential dread. But in cosmic terms, they simply are. They are demonstrations of gravity's capacity to both bind and expel, of thermodynamics' slow march, of the universe's propensity to create structures and then scatter their components. They challenge our narrative instincts that favor story arcs of birth, struggle, and culmination. The Lonely Planet's story is one of violent birth, followed by an inconceivably long denouement, a fade-out that lasts longer than the main narrative of Stars and Galaxies. There is no climax, only gradual change. In this, they are perhaps the most honest representations of the universe's ultimate fate, not a cataclysm, but a slow, cold, quiet dissipation of energy and structure. To study them is to make peace with this scale of time and outcome, to find meaning not in dramatic conclusions, but in the persistence of existence itself, however quiet and isolated that existence may become. It is an exercise in cosmic humility, reminding us that the vibrant, noisy, light-filled epic we inhabit is a brilliant but fleeting moment in a much longer, darker, and quieter timeline, where the default state of a world is to be alone, cold, and silent, carrying within it the fading memory of a more animated youth. The concept of these isolated worlds inevitably leads us to the edges of known physics, to speculative but scientifically grounded realms where the very nature of the planet could be transformed by its environment. One such consideration is the accumulation of dark matter. While the density of dark matter in the intergalactic void is lower than within a galactic halo, it is not zero. The planet, over its multi-billion-year journey, will have passed through a vast volume of space, sweeping up weakly interacting massive particles, WIMPs, or other hypothetical dark matter constituents. If dark matter particles can annihilate with each other, as many models suggest, then a concentration of them within the planet's core, gravitationally captured and sunk to the center, could provide a novel, long-lasting heat source. The rate of this annihilative heating would be minuscule, dwarfed by radiogenic decay for a planet of Earth's mass. But for a larger, more massive super-Earth, or a Neptune-sized object, or for certain enhanced dark matter densities and filaments, It could provide a non-negligible supplement, slowing the planetary cooling by perhaps a few percent over cosmic time. This faint, exotic hearth at the world's center would be a direct link to the invisible component of the cosmos, a hidden fire burning on particles that are otherwise oblivious to normal matter. It is a poetic notion, the loneliest visible object in the universe, warmed from within by the most ubiquitous unseen substance. This process could, in theory, extend the lifespan of a subsurface ocean by billions of years, offering a tenacious, alternative energy source for any deep biosphere long after the radioactive furnace has significantly dimmed. The biology, if it exists, would be ultimately dependent on the cosmological parameters that govern dark matter, its existence intertwined with the secret architecture of the universe in a way that life on a starlit world could never be. Another transformation occurs at the level of fundamental particles. Adrift in the intergalactic medium, the planet is exposed to the full flux of ultra-high energy cosmic rays, UHECers, that have traveled unimpeded from distant active galactic nuclei or other extreme accelerators. Without a protective magnetosphere or thick atmosphere, these particles, protons and atomic nuclei moving at a fraction of the speed of light, would strike the surface or penetrate the ice shell, inducing spallation reactions.
Over eons, this constant bombardment would slowly transmute elements in the surface layers, creating rare isotopes and altering the chemical makeup of the ice. It would also generate a steady shower of secondary particles, including muons and neutrinos, which could penetrate deep into the ocean. For a subsurface biosphere, this constant rain of radiation from above could be a significant source of mutagenesis, potentially driving evolution at a faster pace than the slow chemical gradients from below would suggest. It also provides an alternative energy source. The ionization trails left by these particles could drive radiolytic chemistry in the water, splitting H2O molecules to produce hydrogen and oxidants like peroxides, which microbes could then exploit. Thus, the planet's surface, dead and frozen, becomes a cosmic alchemical laboratory, its chemistry powered by the most violent events in the distant universe, while the products of that alchemy slowly seep downward to fuel life in the dark. The biosphere, therefore, would not be entirely divorced from the cosmos above. It would be subtly connected to it through this slow drizzle of atomic fragments from cataclysms millions of light years away, a whisper of violence filtering down to the eternal night. The ultimate fate of these worlds, in the context of the universe's far future, ties into theories of vacuum decay and proton stability. Some extensions of the standard model of particle physics suggest that the Higgs field, which gives particles mass, may not be in its true vacuum state. A quantum tunneling event could, in principle, create a bubble of true vacuum that expands at the speed of light, rewriting the laws of physics as it goes. For our lonely planet, such an event would be the absolute end. There would be no warning, no visible sign. One moment, the planet exists. The next, it is gone, transformed into something unrecognizable. Conversely, if protons are unstable, as predicted by many grand unified theories, then the very matter of the planet will, over timescales of 10 to the power of 34 to 10 to the power of 40 years, spontaneously disintegrate. The iron in its core, the silicates in its mantle, the water molecules in its ocean, will slowly evaporate into leptons and photons. The planet will fade from existence not with a bang, nor even with a final freeze, but with a silent, gradual sublimation of its substance into radiation. This process would begin in the deepest interior, where matter is densest, and work its way out. For a hypothetical far future observer, the planet would become a faint, ever-cooling cloud of light, its ghostly outline persisting for epochs as the last of its baryons dissolve. In this timeline, the loneliness is not eternal. Even the frozen, persistent artifact is eventually erased. Its long journey ended not by collision or capture, but by the unraveling of the fabric of matter itself. It is a reminder that on the longest scales, nothing is truly permanent, and that isolation itself is a temporary condition in a universe governed by transformative, if immensely slow, processes, bringing our perspective back to the present era of discovery. The hunt for intergalactic planets is also a hunt for a specific kind of philosophical clarity. Finding them would confirm a prediction of our most fundamental models of cosmic evolution and planetary dynamics. Not finding them, despite sensitive searches, would be equally profound. It would imply that planetary ejection is almost never efficient enough to achieve galactic escape velocity, or that such objects are even rarer than we think, placing our own stable solar system in a new light as a potentially even more special outcome. The search is a test of our understanding of chaos and order on a galactic scale. It pushes our observational techniques into regimes where noise dominates and signals are statistical phantoms. It requires a collaboration between planetary scientists, astrophysicists, cosmologists, and experts in data mining and machine learning. The potential discovery would be a triumph of indirect inference, a testament to the power of scientific imagination to conceive of an object and then devise a way to find its shadow. It would be a discovery made not by looking at the thing itself, but by measuring its subtle imprint on the light from objects impossibly far behind it. This is science at its most elegant and patient. A game of cosmic hide and seek where the hider is dark, cold, and almost perfectly still, and the seeker must scour the entire sky with digital eyes, waiting for the one in a quadrillion alignment that betrays a presence. It is a reminder that the universe still holds populations of objects that are not just unknown, but whose very category we have only begun to imagine. Worlds that defy our most basic assumptions about where a world can be and what its nature must be.
In the quiet, persistent search for the loneliest planets, we are ultimately searching for the boundaries of the possible, charting the extremes of existence, and in doing so, better understanding the full, strange spectrum of what it means to be a planet in this vast and varied cosmos. In the tapestry of cosmic phenomena, the lonely planet occupies a unique position as a potential recorder of galactic history. Unlike a star, which undergoes fusion and continually alters its internal composition, or an asteroid in a bound system, subject to space weathering and collisions, the intergalactic rogue is a closed system preserved in the deep freeze. Its value as an archive is unparalleled. Consider the possibility that on its surface, or embedded within its ice, lie layers of accreted material from its journey. As it traversed the outer halo of its host galaxy during ejection, it might have swept up traces of the circumgalactic medium, a dilute gas enriched with the specific elemental signatures of that galaxy's supernova history. Later, during its long voyage, it would pass through the even more tenuous intergalactic medium, potentially accumulating a thin rime of hydrogen and helium along with infinitesimal amounts of dust ejected from distant galaxies. This dust, originating from different galactic environments and stellar populations, would be a microscopic time capsule of cosmic chemistry. A detailed analysis of this accumulated frost, if ever possible, would reveal a stratigraphy of its journey. The inner layers holding the signature of its birth galaxy, the outer layers containing a mixed sample of the wider universe. It would be a Rosetta Stone not for one language, but for many, telling a story of galactic winds, quasar outflows, and the chemical evolution of the cosmos, as witnessed from the unique, mobile vantage point of a dark, silent traveler. The planet becomes not just an object, but a chronicle. Its very body, a manuscript written in the isotopes of atoms collected over billions of years. The gravitational influence of such a planet, while negligible on the cosmic scale, is not zero. In the profound emptiness of a void, where the density of matter is exquisitely low, the planet's gravity dominates a local volume of space. It will have captured, over time, a tenuous cloud of the intergalactic gas and dust through which it passes. This cloud, held in a loose gravitational embrace, would be a miniature, private atmosphere, a coma of isolated atoms and molecules so sparse that particles might orbit for millions of years before colliding. Additionally, if the planet's path were to intersect a wandering, smaller object, a comet or asteroid that was itself ejected from some distant galactic system, it could capture it into orbit. Thus, a lonely planet could, against all odds, possess a moon. This moon would be a companion in the absolute darkness, a silent partner in the eternal journey. Their mutual orbit, undisturbed by external gravitational tides, would be perfectly stable, a slow, silent ballet performed for an audience of none. The presence of a moon could induce a slight, periodic tidal flexing in the planet, providing a minuscule additional heat source and potentially driving a very slow geological cycle. For a subsurface ocean, this could create subtle currents and mixing patterns absent on a solitary world. The existence of such a binary rogue system would be a marvel of cosmic serendipity, a double exile, a pair of lost worlds keeping each other company through the intergalactic night, their gravitational bond the only tether in an ocean of nothingness. Their combined silhouette, if it ever passed in front of a distant quasar, would create a complex, time-variable micro-lensing signal, a signature that would be the ultimate prize for patient observers. From the perspective of the philosophy of science, these objects challenge the very definition of planet. The International Astronomical Union's definition requires a planet to orbit the Sun, a stipulation clearly inapplicable. Broader definitions often include orbiting a star, brown dwarf, or stellar remnant. The lonely intergalactic world fulfills none of these. It is a planetary mass object that has severed all gravitational ties to stellar systems. Is it then a planet? Or is it a new category? An ultra-free-floating planet, a planemo absolutus. This is not mere semantics. Classification shapes our understanding and guides our search strategies. Recognizing these as a distinct class of object would formalize their study and allocate resources to find them. It would acknowledge that planetary science extends beyond stellar systems, into the intergalactic realm. It would force us to consider formation and evolution pathways that are entirely divorced from the circumstellar disk model we have developed from studying our own solar system and exoplanets. These worlds may form in ways we have not yet considered, perhaps directly from gravitational instabilities in the dense, cold gas of a protogalactic cloud, bypassing the star formation stage altogether. They are a reminder that our categories are born of our limited experience, and as we push into new frontiers, we must be prepared to expand or redefine them, to allow the universe to tell us what exists, rather than forcing what we find into existing, possibly inadequate, boxes. The emotional resonance of the lonely planet is undeniable, serving as a powerful metaphor in human culture. It represents the ultimate outsider, the entity that has left the community behind and ventured into the unknown alone. It symbolizes resilience, the capacity to persist in the face of utter isolation and resource scarcity. It also embodies a kind of purity, an existence uncomplicated by the complex interactions of a stellar system, reduced to its core elements of mass, heat, and slow time. For the storyteller, it is a setting of profound atmosphere, a world where the sky is a static museum of distant galaxies, where the only light is a cold, omnidirectional glow, and where the only sound is the occasional crack of ice shifting over geologic epochs. It is a canvas for exploring themes of memory, as the planet carries the unaltered record of its origin, of time, as it experiences it in a linear cooling slide, and of life as the ultimate test of adaptability. In a secular sense, it can be seen as a cosmic monk, having renounced the material wealth and vibrant society of the galactic disk for a life of austere contemplation in the void. Its spiritual practice, the slow conservation of its inner heat against the entropic cold. It is a mirror we hold up to our own fears of isolation and our awe at the scale of the universe, reflecting back a vision of existence that is at once terrifying and serene, a reminder that the cosmos contains every possible extreme, including the extreme of being utterly, magnificently alone. As we conclude this slow, meditative exploration of the loneliest planets, we must return our gaze to the broader cosmos, now seeing it with altered eyes. The universe is no longer merely an archipelago of shining galaxies in a dark sea. That sea, the intergalactic void, is now populated in our mind's eye with a faint, sparse dusting of dark worlds. This changes the character of the cosmos from one of bright cities separated by empty highways to one of a continuous, if incredibly dilute, field of matter. These planets are the faint background hum of the baryonic universe, the bass note beneath the brilliant melody of stars and galaxies. They represent the final state of most planetary mass material, a destiny of cold isolation that awaits countless worlds as galaxies interact, merge, and dynamically evolve over the coming eons. Our own solar system, in the far future when the Milky Way and Andromeda collide, may see some of its outer worlds stripped away and flung into intergalactic space, joining this vast, unseen population. Thus, the study of these exiles is also a premonition, a glimpse into the eventual fate of some of our own celestial neighbors, a reminder that the majestic stability we take for granted is a temporary condition in a universe built on gravity, chaos, and deep time. The search for these worlds is a testament to the ambition of modern astronomy, a field that now routinely pushes into regimes of exquisite faintness and incredible precision. It requires a synthesis of cosmology, planetary science, gravitational physics, and data science. The tools for this search are now being built or conceived. The Vera C. Rubin Observatory, with its relentless all-sky cadence, the square-kilometer array with its sensitivity to the faintest radio whispers, the next generation of space-based infrared observatories that might one day detect the thermal glow of a relatively close, still warm rogue in the galactic halo. Each new instrument extends our perception, allowing us to see fainter, cooler, and more distant objects. The lonely planets between galaxies represent one of the final frontiers of direct detection, a benchmark for our technological and inferential prowess. Finding them will not be a single eureka moment, but a gradual accumulation of evidence, a statistical anomaly in a microlensing survey, an unexplained point of faint infrared emission in a dark field, a peculiar signal in a weak gravitational lensing map. The discovery will be announced in the cautious, precise language of astrophysics, in a paper filled with probabilities and confidence intervals. But its implications will resonate far beyond the pages of a journal, changing our sense of place in the cosmos and expanding the domain of where we imagine worlds, and perhaps life, can exist. In the quiet of this contemplation, we are left with a profound sense of scale. The journey of a lonely planet is measured in billions of years and millions of parsecs. Its internal processes unfold with the patience of geology multiplied by the isolation of the void. Its potential biosphere, if it exists, thinks and evolves on timescales that make human history look like the briefest spark. To hold this concept in mind is to perform an act of temporal and spatial dilation, to stretch one's imagination to its limits. It is a form of cognitive therapy against the myopia of daily life, a reminder that the universe operates on stages so vast and timelines so long that they defy human intuition. Yet, through science, we can reach out and infer the existence of these distant dark travelers. We can chart their probable paths, model their internal workings, and dream of ways to find them. This ability to conceive of and search for the nearly invisible, the almost impossible, is the great gift of the scientific narrative. It allows us to map not just the bright and obvious, but the dark and subtle, filling in the blank spaces on our cosmic maps with reasoned inference and patient observation. Ultimately, the lonely planet between galaxies stands as a symbol of cosmic resilience, It is a survivor of gravitational violence, a bearer of primordial secrets, a potential cradle for life in the most unlikely of places, and a future relic of an age of light. It is a world that has traded the vibrant community of a galactic disk for the ultimate independence of the void. In its silent, endless journey, it carries the story of its birth, the record of its travels, and the slow, patient energy of its decay. It asks of us only that we look deeper into the dark spaces between the lights, and consider that in the great cosmic story, solitude is not an emptiness, but a different kind of fullness, a state of being where the universe whispers its secrets in the language of cooling rock, frozen oceans, and the faint, persistent tug of gravity in an expanding, evolving, and ever mysterious cosmos.